Hello everyone, in this video we're going to take a look at some of the ideas surrounding integration by parts. Okay, so what is this all about? Well, it's a method for solving problems about integration. So it's something every scientist should have in their toolbox so they can solve integration problems. And you can think about it as it's the opposite of the product rule for differentiation. Okay, so we know that differentiation and integration, they're opposite to each other, they reverse each other out. So if we take the product rule for differentiation and just integrate it, then we get a new equation, which is the parts formula. Okay, so let's derive it. So this video, it's going to be more theoretical, talk about where things come from and how to use them. So let's spend some time deriving this. So the product rule, so let me just say firstly, the parts formula typically uses U and V. So let's apply the product rule to U times V. I'm sure you all have your own way of this. For this, I think about it as differentiate the first one, so differentiate U, keep the second the same, and then keep the first one the same and differentiate the second one. So that's the product rule. So what we're going to do is rearrange this and make the subject U dv dx. So U dv dx is the same as differentiate U times V, subtract the U dx times V. So all I've done is take this term here and isolate it, and I've done that by looking at the term in front of it and moving it to the other side by subtracting itself from both sides of the equation, and then I've just written the thing you can see circled. I've written it first, it just appears here. Okay, so now I'm going to integrate both sides. And I'm going to remember that integration is the opposite of differentiation. So if I differentiate something and then I integrate it, let's get back to the start. Okay, so let's do that. So we have the integral of that thing on the left hand side, the integral of this. Now integrate the other side, so I need to integrate the first term and then integrate the second term, second term being this one, and then I notice that this term here is just UV because the integration and the differentiation reverse, and the second term, well, that just stays where it is, that's fine. Okay, so this is the parts formula. It says if you integrate U times dv dx, the answer is the same as U times V take away this integral over here. Okay, so let's write that on a clean page and spend a few moments thinking about applying it into certain scenarios. So what we just showed was, if you take the product rule, integrate both sides, and just rearrange things a little. There's a U there. You get this formula. So this is your parts formula. It's worth remembering, because I think if you remember it, you've got much more chance of solving problems. Nothing worse than flicking through a formula book. Just kind of suggests maybe you don't know it that well. Let's tidy this up. Okay, so there's your parts formula. So what patterns can we see here? Well, I suppose the first thing to notice, this method can be used when there's a product. So if we have some product and we're integrating, you should be hearing alarm bells going off in your mind. This looks like parts. Maybe I can use the parts formula. So that's the first thing to notice. If you're integrating a product, spend some time thinking about, can I use parts? Next thing you need to do, you need to think about your labels. It'd be nice if it was F and G. It's not that simple. Or U and V. Again, it's not that simple. The labels should be U and dv dx. Okay, I would always write them going down like this. If you keep your answer in a familiar format, then it's much more likely to not make silly mistakes. Okay, so what's on the other side of the equation? Well, we need U. We already have that from our label. And we need a V. Okay, well, we don't have V at the moment. So wherever we label here, we need to find V. So how are we going to find V from dv dx? Well, you're probably going to have to take a good guess or integrate it. You have to integrate dv dx to reverse out the differentiation. Okay, what else can we see? Oops. We can see there's two things inside this integration. The first one is, that jumps out to me anyway, is the V. We already got that, that's fine. We also need du dx. Okay, so we have u, whatever that is, we have to differentiate it to find du dx as part of our formula. So I can't stress it enough, really. If you label your answer this way, you don't even need to remember the parts formula. You just need to know your times in this way, u times v. Then you're taking away the integral of the two functions times together on the right hand side. So for me, it's just a nicer way to remember the formula. Just follow those two arrows, u times v, take away the integral of du dx times v. Okay, that's just a labeling exercise, really. So what about the problem itself? What's actually going on a much deeper level? Well, we're taking something with a u in it. So I've already heavily labeled here, this one here, and we're changing it to a du dx. So ideally we want u to be something that differentiates to something else that's much simpler. So for example, if u was x this would be great, because if you differentiate x, it goes to 1, and hopefully this integration on the right will be much easier. Also, something to think about, this dv dx, you need to extract v from it. So you need to choose something which you can integrate. So for example, if this was some maybe natural log, if you labeled that as dv dx, you'd be in a bit of trouble if you were starting from the beginning with these ideas, because log of x isn't a standard integral. So you need to keep that in mind. Whatever you label there, you're going to have to integrate and put on the other side. Okay, so really that's the hard part of this method, finding the labels, which is u, which is dv dx. I think the thing I like most about this is it's 50-50. If you think the first factor is u, and you go through and it's not right, well then just go back and swap them over. U is either the first or the second. Okay, so if you're in a rather desperate situation, just guess. If it doesn't work, go back and swap. Okay, of course we're not going to do that. We're going to know how to solve, because we're going to do lots of practice. Anyway, let's look at some examples. Let's start to really understand this formula and this method. So the first example, really I'm just trying to understand the method more than problem solve at the moment. All the examples, the detailed examples, are going to follow later. So integrate x sine x. Well, I can see there's a product, so I should be thinking use parts. And I know with parts, I need to think about labels. Typically, it's easier to think about which is u. Okay, the other one then, we'll just drop in for dv dx. So is it x or is it sine x? Okay, well we know the formula for parts involves a du dx. So wherever we label for u, we're going to differentiate it. Pick the one that differentiates to something simple. So choose x. Okay, so the labels, u is x, dv dx is sine x. Remember, the dv dx, we need to be able to integrate it. We can integrate sine, so this seems like the right choice. So find the other pieces of the puzzle. Differentiate u, so differentiate x with respect to x is 1. For this one, I must admit, I tend to just guess. Pick some v which differentiates to sine. I don't know, probably cos or minus cos. Cos differentiates to minus sine. So my guess didn't work, but I can fix it. It's minus cos. Actually, it's a standard integral. But for some reason, it just doesn't stick in my head. Just take a guess and I check it, or use your standard integral. Okay, so that's v, integrating sine. And at this stage, let me say, you don't need to add c, your constant of integration. We're just trying to find something that works, not capture every answer, just something that works. Okay, so parts formula. I'm going to label my question I for integral. I is uv take away, let me remember, du dx times v integrated. Okay, so u times v, I'm just following my usual pattern, is x times minus cos x. Take away some integral, and I know the integral is just the product of those two. So it's 1 times minus cos x dx. Okay, so I'm going to simplify a little. I'm going to put the negative at the front. negative x cos x. And it depends how confident you are with the integration. There's a negative here and a negative here. So you could just integrate cos x. I think I'm going to write it rather than do it. Okay, so the negative comes to the front, so positive. And then on the next step, I'm going to do the integration. So this was my safety net. If I don't make a mistake, I pick up some marks. If I jump too quick, I could lose a few marks. So I really want to set my answer out as a story. Okay, so finally, integrate cos x is sin x. And I want to capture all the answers. So finally, I'm going to add the constant of integration. And there you go. There's your answer. The integral of x sin x is this thing. Minus x cos x plus sin x. And you can add on any c and that will work. Okay, so what actually went on there? Well, we simplified this thing, so integrating x sin x, to a slightly different problem. 1 times minus cos, and this one was much easier to integrate. Okay, so there's our first example. Let's try another. How about integrate x times the natural log of x? Okay, so straight away we can see this x times log x, so it's about some product. So straight away we think, oh, this looks like parts. So next I should be thinking about my labels. So which one is u? Is it x or is it the natural log of x? Okay, so the last example is kind of misleading us a little. It's kind of suggesting use x, that works, but it's not always the case. Let's see what happens with this one if we label u as the x. Well, if we label u as x, the v dx must be natural log. Calculating the other pieces, so differentiate x, we get 1. What is v? So we need to integrate log x. Well, I do know it, but it's not a standard one. I spent a fair few years getting good at calculus before I could rattle that off without any calculations. So we just don't know. Okay, so it didn't work in this case. The whole thing, it didn't work because we cannot integrate the v dx to find v. So there's only one other option left over, and that is to call u equal to log of x. So let's just see what happens here. So this means that the v dx must be x. Calculate the other pieces. Okay, differentiate log of x. This is a standard derivative, 1 over x. Well, that's quite nice, the log disappears. And if we find v, you can either guess something like x squared. If you differentiate x squared, you get 2x. Just halve it, that fixes that problem, or just integrate x squared over 2. Okay, so my integral is uv minus du dx v dx. I don't memorize that formula, that's why it takes me a minute to think about. I'm thinking about my arrows. Okay, so u times v is x squared over 2 log of x. Now here's the thing we want to work for us. I want to multiply these, and I want something that I can integrate. So 1 over x times x squared over 2. Can I integrate this? That is the key to solving this problem. And if you look at it, it's actually really nice, because the x's, well, there's some cancellation. There's a 2, we could bring it to the front. So actually what we're left with over here, so this thing, we're actually left with integrate. Okay, I'll take the half to the front, and we have x dx. So wow, we end up having a problem of integrating x, which is significantly easier than integrating x log x. Okay, so I'm not going to finish that off. I think I'm just trying to collect ideas. We can see the answer though. It's x squared over 2 log x. Take away a half, and then do the integration, x squared over 2 plus c. Okay, so really just trying to spot patterns, and the message, if you see an x, you'd like it to be the u, you'd like it to be the u label, but it's not always true. We have to make sure that we can integrate what's left over. In the case of a log, it's normally the other way around. We normally have to choose the u label as log, the natural log. Okay, so like I said, just idea collecting at the moment. All the problem solving and the examples will come later. So just want to move on a little bit next to integration with limits, still by parts, but with some limits. So integration has some important geometric meaning. It's the area under the curve. So what happens if I have a problem and I want to use parts, but we have limits? So here's the formula without the limits. So what if I add on integrate between a and b? So what do I need to change, or add I should say, to the right hand side? Well, a and b appear on that integral. What about this uv? People just typically write a vertical line and put a, b, and then it's understood as evaluate between a and b. So put b in, put a in, and then subtract them. This is the way that people, scientists, typically solve these problems. So just to demonstrate that, let's pick something. We've already looked at x, sine x. Okay, let's pick some limits. 0, pi over 2, why not? We've done this one already. We saw the labels where x is the u, and the sine x is the dv dx, and we've been through the whole process, and we showed that maybe I'll just I'll write it here. We have shown that the integral is, let me remember, minus x cos x. I don't remember the other bit. Let me think. Plus, actually, oh, let's just do it. Oh yeah, let's just do it. I don't remember. Okay, so du dx is 1. V is minus cos. So x, so that's that 1 u times v minus integrate minus cos x times 1 dx. Okay, so that's the bit we've shown. Okay, so now I'm going to add my limits. So the problem is actually between 0 and 2 pi. So I'm going to put on my, not 2 pi, pi over 2 I mean. So I'm going to put my 0 and pi over 2 on there, and I need to evaluate that first term between those limits. Okay, so to do that, for the first term I put in pi over 2 and calculate that. For the second term, then I put in 0, evaluate that and subtract. And then in the second term I need to do some integration. So I need to, if I just study the pattern here, we have a minus and a minus. So integrate cos x, which is sine x, and that goes to a plus. Between pi over 2 and 0. And if I go to the next page, well, let me just calculate these before I do that. So if I put that into a calculator, actually cos of pi over 2 is 0, 0. This one's just 0. So actually, I think I can just squeeze it on. Sine of pi over 2 minus sine of 0. Sine of pi over 2 is 1. Take off sine of 0, which is 0, giving me the final answer of 1. Okay, so there you go. That's the answer with the limits. So the integral x sine x between 0 and pi over 2 is 1 unit squared. Okay, so very similar to before. We just need to evaluate each term, the uv term and the integral on the second term. Okay, so more examples of this will follow in later videos. The next thing I want to do is look at some advanced questions. So it might be something to refer to later if this is all quite new to you. Just to keep in your mind for the moment. There are some quite tricky questions using parts. The first one is repeated applications. So repeatedly using the parts formula. So let's just say a few things about that. Just before I do that, if you find this idea is a little tough, maybe still quite new, I would recommend having a break. If you feel confident with what I've said so far, now is the time to step up to the next level. Look at these more advanced questions. Let's take a look at integrating x squared sine x. Okay, so what do we see here? Well, I could label the x squared as u. So if I differentiate that, I have 2x. Forget about the 2. Constants are never particularly an issue. And if I integrate sine x to find v, this will be cos x. Again, I'm not worried about the sign, if there's a negative or not. That's not a big issue. Applying the parts formula, then, so we apply parts. I'm not going to do it. I'm just going to say if we apply it, then the problem is going to involve integrating x times cos x. So where does that come from? Well, when you differentiate the x squared, you get 2x. Forget the 2, it's just going to have some x. And when you integrate sine x, you're going to get cos x. Okay, there might be some sine in there, not too worried. I put it in the parts formula, then I'm going to have to integrate x. I'm going to have to integrate, yeah, x cos x. That's what I want to say. The problem's going to involve integrating x cos x. Is that much easier than the original problem? Well, yeah, it is, without doubt. Because if I apply parts again and I label x as the u, then the u dx is 1. So if I apply parts again, the problem is going to involve differentiate x is 1, integrate cos, forget the sign's just going to be written at the front of the integral. We have a problem of integrating sine, which we can do using standard integration. So the reason why this one is so tough is because of the squared. We apply parts once, it's going to drop down to a single power, and then we apply it again, and the x is going to disappear, and then finally we can integrate. So this one's quite a tough one, using repeated application of the parts formula. And typically, if you have some power of x in front of sine, every time you use the parts formula, that power is going to reduce by 1. So you're going to have to use parts n times to solve this. So it's going to get very, very messy for large n. So I just want to highlight that some of these problems you might need the formula twice. It doesn't get prettier, I'm afraid to say. There are also some tough questions that don't involve repeated application. The way that I think about these other tough problems is the reciprocal. They're on a cycle, cylindrical, or however you want to think about it. They're going round in some circle, and let me show you what I mean by that. So these are probably the hardest problems you can encounter for parts, which I'll go into much more detail later on in the problem solving videos under the advanced section, without doubt. So something like sine x e to the x, this is a nasty problem. So what can we see here? Well, the e to the x, if you call this u, if you differentiate it, it stays the same. E to the x differentiates to e to the x. If you call it dv dx and you integrate it, again it stays the same. Not much is going on. You cannot get rid of that e to the x by integrating or differentiating. How about the other term? Well, if you call it u, differentiate, it's going to go to cos. So let's put that into the parts formula, and the problem is going to reduce to integrating cos x e to the x. If you put it into the formula, the du dx goes to cos, the v goes to just e, and it feels like we got no further. Okay, all that's happened is we got a more complicated equation which involves integrating cos x e to the x. Now the really interesting thing is, if you do it again, well, the reason why I think of these as being on some cycle, e to the x isn't moving, but if you label this one, this cos as u, then du dx, well, it's negative sign. Forget the negative for the moment, we can just take that outside the integration. It goes back to the beginning. We end up with a integrate sine x e to the x problem, which might feel a bit strange, like you're going around in a circle, but actually it's great news. What you'll see if you try to solve these advanced problems, you can have your problem, let's call it I. You're going to have some mess, and then you're going to integrate it again. you can have more mess, take away your answer appearing, and using that parts formula, your answer is going to appear again. And actually, this is brilliant news, because you can rearrange this to get I on its own. So if you take the minus I to the other side, you have 2 lots of I equals a lot of mess, and you divide it by 2, you get I equals a load of mess, and that's your answer. In here, you're just going to have lots of x's and functions and various other bits, and it turns out that the answer will just drop out for you. It's not very clear at the moment. I'm just talking about ideas, but later on you will see when you start looking at these advanced questions, you should keep your eye out for things that appear on cycles, and be aware that of this advanced technique. So I think I'm going to end it there. I've gone from some quite simple ideas to the most advanced in just over half an hour. So the next thing to do is problem solving, and I'm going to do that from day one, start from right from the beginning. I'm going to do lots and lots of examples that slowly develop right up to these advanced ones. Okay, thanks for listening. Check out some of those later videos to help you build your confidence for your problem solving. Any comments, of course, just leave them in the comments section. Feel free to subscribe for more videos. I'm going to keep adding them over time. Just going to keep building banks and banks of questions, which I think are of great value if you're studying this. So yeah, thanks for listening, and goodbye.